Hello everyone, in this video we are going to discuss the fourth problem which came in BMath BStat 2022. So the problem says that let px be an odd degree polynomial in x with real coefficients. Show that the equation p of x equals 0 has at least as many distinct real roots as the equation p of x equals 0. So before jumping into this equation, you must note one thing about the odd degree polynomials, that is their range is the whole of R. So if p of x is a n x to the power n plus a n minus 1 x to the power n minus 1 plus dot 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 a1 x plus a naught, then if now n is odd, now if an is positive, then when x tends to infinity, positive infinity, x is very very large, the leading coefficient is positive, and so the polynomial will be tending towards positive infinity. And when x is tending towards negative infinity, and so then the polynomial will be tending towards negative infinity because n is odd here. Okay, and a polynomial function, so it's continuous, and thus it takes its range is all of R. So any odd degree polynomial has its range to be the whole of R, the reals, I mean. Okay, so fine, it's all of R. And now how does that help us here? So now here in this statement, look at this, that is p of x equals 0 has at least as many distinct real roots as the equation p of x equals 0. Okay, so let's consider the distinct real roots of the equation p of x equals 0. So let x1, x2, dot 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 xk be the distinct real roots of p of x. Okay, and now what we can say here is, since they are the distinct real roots of p of x, so now for each of them, if I want to get a root of p of x, okay, so I have to show that this p of x equals 0 has at least k distinct real roots. So corresponding to x1, I have to bring 1 0, like one value where p of x will be 0, and so on and so forth, and they must also be distinct. Okay, so what I can do is here, if I can simply just get hold of x1 here, then it will again become p of x1 and it will become 0. And now that's the beauty of this problem. So once you realize the first step, that is the range is whole of R, it's done. So since the range is whole of R, so x1 is also a real value, right? And so corresponding to it, we will have some value yj, where corresponding to it, the p of yj is equals to xj. Okay, so for all j going from 1 dot 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 till k, there exists yj such that p of yj is equals to xj. Okay, so at y1, the polynomial px will take the value x1, because the polynomial will take every in its range x1 is there, so there has to be some value y1 for which x1 is being attained, and then y2 for which x2 will be attained, okay, and so on till yk for which xk will be attained, and all these points will be distinct because you can't, I mean, it's a function, right? So you can't have like for example, like a particular, like for example y1, for y1 the polynomial is taking two values, that is some x I and xj, okay, it can't happen because it's a function. And so where we have yj's to be distinct, okay, and so thus we have p of yj is equals to p of xj and is equals to 0, and thus p of x has at least k real roots, okay, and p of x was also having k distinct real roots, and so p of x is also having at least k distinct real roots, okay. We can say at least k distinct real roots, not exactly, okay, we don't know whether it will have more than that or not, just we have proved that, yeah, according to the problem, at least k real roots, and thus we are done. So I hope you like the video. So thanks for watching, and see you in the next one.